So at this point in Chapter 4, we've covered changes in motion. Now we're moving on to Newton's first law. Let's take a look. Newton's first law discusses inertia. Inertia is defined as the tendency of an object to keep doing what it's doing. In other words, if the net force is zero, there's no external force being exerted on the object, then the object's acceleration will also be zero. That's known as inertia. So let's look at two different examples. In example 1, we have a book that is at rest on the table. This means that the net external force on the book is zero. If we want to label a free body diagram, we can see that the book's weight is pushing downwards. This upward force from the table is balancing it out. That's what keeps the book still. Inertia also functions in situations with constant velocity, again where the net force equals zero. In this case, we have a block that is being lowered downwards on a rope. The block's weight is going down in that direction, but at the same time, the force of the rope, we'll call that R, is pulling the block upwards. Having these forces balanced allows the block to continue at a constant velocity. In order to study inertia, we're going to define the net force on an object. The net force is the vector sum, so we'll be going back to vectors like we studied in Chapter 3, of all forces acting on an object. Let's look at this situation where we have a block being pulled forward, and we'll draw an FBD for the block to make this a little bit easier to understand. Here we have the weight of the block. We have some kind of upward force from the ground. I'll call that U for upward. Then we have the force of this rope pulling forward. I'll call it R for rope. As you can see, the upward and downward forces cancel out, and we're left with the force of the rope. That is the net force, a force pulling forward, or in the right direction, that's carrying the block across the table. So another thing to keep in mind is that inertia is directly related to the object's mass. If an object has a larger mass, there's more inertia, which means that it requires a larger force to move that object. Let's take this example with a small car and a large truck. Say we have a man who wants to push the car. The car will be hard to push, but ultimately it will take much less force to accelerate the car. In the case of the truck, we would need a much bigger and much stronger person to exert much more force to cause the truck to go forward. That's because the truck has such a great mass in comparison to the car. Let's look at another useful term in our study of inertia. This word is equilibrium. Equilibrium describes objects that are at rest or moving at a constant velocity. In other words, objects where the net force acting upon them is zero. Let's take a situation with a dog on a leash. The dog is walking at constant speed. This is because as the dog pulls in this direction on the leash, the owner's hand on the other end of the leash is exerting equal force on the dog. This means that the net force on the dog is zero, and the dog will proceed forward at a constant velocity, because no matter how hard it pulls, its owner will pull back with an equal strength. Now let's do some practice from this section. If all of the forces acting on an object balance so that the net force is zero, then A, the object must be at rest, B, the object's speed will decrease, C, the object will follow a parabolic path, D, the object can change direction but not speed, or E, none of the above. So I think we can eliminate a few of these answers right off the bat. Let's look at answer C, the object will follow a parabolic path. Well, we've mentioned nothing about parabolas in this chapter, or the path that an object will follow. So C is easy to eliminate. Now let's look at B, the object's speed will decrease. Well, we know that some sort of force is required to change the speed of an object, and if the net force is zero, then that answer can be eliminated. Let's also look at D, the object can change direction. Let's say an object is traveling to the right. In order for it to change direction completely and move back towards the left, there would need to be, say, a wall or some other sort of external force to push the object back the way it came. That means it can occur if the net force is zero. Finally, we'll go to choice A. The object must be at rest. It's true that in situations where the object is at rest, the net force is zero. But the net force can also be zero on an object that's moving at constant velocity. Therefore, A is also not the correct answer. We're left with E, none of the above. That's the answer to this problem.